Okay, so it's exactly 1 p.m. and we can make a start. Welcome all. I will begin by going through the webinar housekeeping. So this webinar is being recorded and the recording will be made available through our page on YouTube and circulated via the emails that you used to register. All participants will be muted except presenters, but we do encourage your participation, so please feel free to post any questions in the question and answer function. My colleague Amy and I will moderate the questions after the presentation, so please make use of this function. So just running through the agenda, I would like to take this time and welcome you all to this webinar based on the research report, Gas Compressors for 100% Hydrogen Duty. We have 190 people registered for today, so once again, thank you very much for your expressed interest. I will quickly introduce myself. My name is Chim Kamwela. I am a technical officer working on energy transition for the Energy Institute, and I will give a broad overview of the Energy Institute, or the EI, followed by Professor Ian Arbon from Engineered Solutions, who will cover the key findings and details from the research report. So Engineered Solutions were contracted to carry out this piece of work, which was published last week. So for those that have never heard of the Energy Institute or joined one of our webinars before, we are a chartered professional membership body for people who work across the energy world. And we are a registered charity with over 20,000 individual members, 120 company members, 44 technical partners, and more than 100 technical committees and sub-working groups. We were formed in 2003 as a merger between the Institute of Petroleum and the Institute of Energy. So technically, before transitioning, we've been around for over 100 years. So as part of the EIS 2030 strategy, the EIS role is threefold, and those are the 3 points shown on your screen. We deliver our role through offering a variety of training courses, both short and long, covering topics like energy fundamentals, for example. We engage and support the next generation of industry leaders through a Young Professionals Network, otherwise known as the YPN. And we also publish various content on energy topics through one in-house magazine known as the New Energy World. We also host key events, including an International Energy Week, which brings together experts in the energy industry. And our next conference will be held in February of 2025. So we also manage technical committees, host webinars such as this very one, and hands-on workshops to foster learning and collaboration. We collaborate with institutes and associations and other industry bodies as well. And we produce research reports and practical guidance with a strong focus on energy transition. At the EI, we have an academy as well, which was launched and offers expert-led training courses and free learning resources across a wide range of topics for all levels of capability and experience. And in this case, the EI Academy can support your professional development journey by helping you upskill or reskill for the energy future. So on this, the EI has a growing portfolio of training courses in hydrogen. So two notable courses to mention our hydrogen-based system courses. Both of them are self-paced online courses, which you can complete in your own time, wherever you're based in the world. And we also offer a shorter, more introductory course that covers essential concepts, international context, emerging markets, and key hydrogen technologies. And we also offer an extended version of this course, which additionally covers current hydrogen applications. Just to mention as well, our training team are always keen to know more or hear more from our audiences as to what training you're looking for. So if you would like to discuss your training needs, please do get in touch with us by scanning the QR code or following the web link on the screen as well. So with various departments at the Energy Institute, we have our Technical and Innovation Program on which the hydrogen work is focused. And the aim of the Technical and Innovation Program is to accelerate the transition through collaboration in diverse energy sectors with a more recent proactive shift towards low carbon. And our program covers a wide range of topics from hydrogen, CCUS, power systems, aviation, onshore wind, offshore wind, and many more that you can actually see on the screen. And with all these topics, we have over 800 titles, both research reports and good practice guidance, ranging from HSE risk management to lab test methods, with over 50 titles published annually. So sitting under our technical and innovation program is the Hydrogen Committee. So I will let you know that our Hydrogen Committee was set up in November of 2019 when key themes were identified at the stakeholder workshop, notably CCUS, hydrogen, and integrated power networks. So our hydrogen program took about a year to set up and is now almost 5 years established. So just over 2 weeks ago, we held our 14th committee meeting, and this just shows you how far we've come. So the committee comprises of 40 plus members, including energy regulators, academia, and independent experts as well. And our committee looks to help identify and address the regulatory, safety, and technical challenges facing companies wishing to be involved with the hydrogen space. So this is just an example of how our publications look after being published, and the topics range from asset integrity and repurposing to separation distances, energy balance, skills gaps, compression, which is the topic for today, and many more. And if you would like to find out more or get involved with any of the projects on hydrogen, please do get in touch with myself after the webinar, and the email details will be displayed at the end. So at this stage, I will hand over to Professor Ian Arbon, who will introduce himself and also cover the main agenda item, which is the research report. So over to yourself, Ian.
Yeah, okay, thanks very much, Chim. And let me also add my welcome to all participants. Thank you very much for attending. Next slide, please. Just a personal introduction. I'm an unusual combination because I'm a career businessman, chartered engineer, chartered environmentalist, and part-time academic. So I address this topic from much more than the viewpoint of a single vested interest, and that's fairly unusual in my experience. Spent more than 50 years in manufacturing industry, mostly in the UK, but also in Netherlands, Germany, USA, starting as an apprentice, working through many roles in industry before moving into senior corporate management. And relevant to this particular webinar, in the course of my career, I have been managing director of both Arbon compressors in Glasgow and of Peter Brotherhood in Peterborough, both UK compressor manufacturers who and they will both feature in parts of this presentation. But for most of those 50 years, I've been involved in supplying gas compression equipment to the energy industry around the globe, and particularly in hydrogen service. So I know this sector really well, which I find, talking to most people, is fairly unusual. For the past 28 years in our company, Engineered Solutions Consultancy, we've become heavily involved in sustainable engineered systems, and in particular their impact on the global climate and ecosystems. Next, please. So coming to the hydrogen compression report that we're here to talk about, I'll briefly introduce it. Next. So you can see the front page of the report there, as Chim said, was published last week. And it's the work of the Energy Institute's working group, HY 2306. And the brief the working group was given was to investigate and to verify the data for gas compression requirements contained in the Energy Balance Research Report, which I'll mention in a minute, and to determine the exact requirements for gas booster compressor stations operating on 100% hydrogen. I think we did all of that and have done a bit more in the report, but I think we've covered the brief. Now that's quite a long brief, and we've come up with a snappier title, which is Gas Compressors for 100% Hydrogen Duty. And throughout the report and in this webinar, we will refer to it as the Hydrogen Compression Report. So the report was commissioned from Engineered Solutions, our company, and was published last week, as we said. Right, just before that, they were intended. Sorry, you can go back. Yeah. Um, uh, these were intended to be issued more or less simultaneously, but the New Energy World published this article a few weeks before, and I was commissioned by New Energy World to write an article to support the report called "Hydrogen Compression: The Missing Link in the Hydrogen Value Chain," and I think this is really important to understand because I speak to many people in the hydrogen industry, and almost all of them are very busy with projects on the production side and on the consumption side. But I speak and meet very few people who are actually dealing with the bit in the middle, which joins the two sides together. And without that, we can't possibly have a hydrogen economy. So I think this is a very timely report because it's addressing that crucial interlinking of what everybody else is doing. So the blurb in this article was the main technology involved in joining the production side to the consumption side in the hydrogen value chain as a gas compressor. These are examined in the Energy Institute's new research report, Gas Compressors for 100% Hydrogen. The new report identifies 6 typical major applications, as we will see, ranging up to very large flow rate compressors for gas pipelines and geological storage, where the biggest unknowns exist currently, and I'll explain more of that later. Next, please. So in the article, we say, in a bid to fulfill international ambitions to combat climate change by reducing greenhouse gas emissions, there's been a proliferation of hydrogen projects in what has become known as the hydrogen value chain in the past few years. But these are often localized projects with little by way of national or international coordination, which has led to most of these projects being located either production or consumption sectors of the value chain. And while there are certainly many worthwhile projects in both of these sectors, and I'm not in any way denigrating them, little thought appears to have been given to how the two sectors can be joined together. The answer, to a great extent, is hydrogen compression systems. So it's perhaps surprising, at least to me, that so little attention has been given so far to this crucial link in the chain. I say again, without compression, this is not going to work. And we've got an awful lot yet we need to learn on that compression duty. Next. Next, please. So I just wanted to spend a little while talking about the energy balance report that this was originally based on. Next, please. So here you see it. We had a rather unwieldy title on this one, but which might explain why it hasn't been a bestseller. But application of life cycle assessment methodology to the understanding of the energy balance and efficiency of hydrogen value chain building blocks. We now generally know this, and we refer to it in the report as the energy balance research report. I had the privilege of being the chair of this particular working group, and it was breaking a lot of new ground in looking at whole life cycle assessment, which isn't commonly done in projects like this. So I'd certainly commend it to you. This report was commissioned from Genesis Consulting, and it was published in May 2022. So it's been around for over 2 years now, and we drew very heavily on it in our current report. Next, please. So the background to the energy balance report was global imperative to significantly reduce greenhouse gas emissions has led to growing interest in the role of hydrogen in the energy transition. With the UK's legally binding targets to achieve net zero by 2050, understanding the efficiencies and emissions of hydrogen in comparison to other fuels and or energy vectors is paramount for informed decision-making in energy policy. The Energy Balance Report aimed at comprehensively analysing the energy balance and efficiency of the entire hydrogen energy system, from production to consumption within a UK setting. The study was conducted in 3 specific areas of the value chain: production, transmission, storage, and distribution, as well as usage and consumption across various sectors: electricity, heating, and transport. Next. The goal of the Energy Balance Report was to understand the efficiencies and or inefficiencies of the whole hydrogen energy system and quantify the energy intensity and associated greenhouse gas emissions compared to other fuels and energy vectors, providing an independent, holistic view of all options from production through transmission to utilization. Observing that many studies recognize only localized data, every effort was made in this study to utilize whole life cycle analysis, or LCA. Yes, please. I just wanted to put in a disclaimer here, lest anybody think otherwise. As with all Energy Institute publications, great care was taken with both reports to accurately present the salient facts emerging from the research to enable correct decision-making to be based on presented facts. These reports do not presume that hydrogen is the correct answer to the question, as some do, but they present data to enable readers to make their own informed decisions. It's not part of our role to push hydrogen, but to say what you need to consider if that's what you have decided is the right answer for your project. There was no pressure from any quarter on either report to influence the data presented in them or in any way to support other predetermined decisions made without the relevant facts having been available and considered. And next, please. And just an update regarding COP28, because that was after the Energy Balance Report was written or published. Until recently, energy efficiency has been a largely overlooked area of the energy transition and indeed of UK energy policy, with some practitioners claiming that it is a less important measure than others. However, the largely unexpected wording of the pledge signed by the UK and many other countries at COP28 in Dubai in December last year, that we, quote, must double the global average annual rate of energy efficiency improvements from around 2% to over 4% every year until 2030, unquote, has raised the significance of energy efficiency to an unprecedented new level. And although published well before COP28, this pledge has made the Energy Balance Report of even more relevance to the hydrogen value chain. And indeed, I spoke on this very subject at the International Energy Week earlier this year. Next, please. So, the first step in the hydrogen compression report, which we're considering now, was to verify the data in the Energy Balance Report. So next, please, we could just look at this briefly. Probably, in terms of gas pipeline transmission, probably the most significant finding from the Energy Balance Report for the new hydrogen compression report related to gas pipeline transmission, Section 5 of the EBR clearly demonstrates that to transmit the same energy value, and I've underlined that because this is the bit that I think most people are missing, to transmit the same energy value as we do today, the gas pipeline pressure losses and booster compressor drive power requirements are very much higher for 100% hydrogen than for the original natural gas for which they were designed. This is shown clearly in the 2 following tables. Next, please. So these are tables taken from the Energy Balance Report without alteration. And the first one shows they are repeated in the new report when you are able to look at it. This shows transmission pipeline pressure drop per kilometre for 100% natural gas, 20% hydrogen blend, and 100% hydrogen. And you can see that we're looking at those three cases, operating pressure in each case being between 40 and 70 bar at suction and discharge. And the main thing I want you to notice here is the flow rate measured in million standard cubic feet per day, which is an industrial American measure, which we don't normally use, but it seemed the right measure at the time. And you'll see that for 100% natural gas, again, for the same energy value, in all cases, we were compressing 1,500 million standard cubic feet per day. When we move just to a 20% hydrogen blend, we need to allow for that dilution of energy transmitted in the gas flow. And so that figure rises to 1,743 million standard cubic feet per day. And when we go to 100% hydrogen, and this was the bit that we found quite startling in this report, we need as much as 4,877 million standard cubic feet a day just to get to the same the same flow, the same energy value in the flow. Sorry. Next, please. Right, this was the second table I was referring to, the power requirements. And you can see the result of this. If we just look at the first column, well, the second column in booster power, this is the compressor in the gas booster station in megawatts. And for 100% natural gas, the drive power was 39 megawatts. For a 20% hydrogen blend, it rose to 48 megawatts. And for 100% hydrogen, it rose to a whopping 170 megawatts. And you can see in each of those cases, the energy flow is exactly the same. So with differentials like that, this is not something we can possibly ignore. And yet, we still see reports coming out from different bodies doing just that, ignoring the likely consequences of this. The other factor is that in the fourth column across, the number of booster stations required for a given length of pipeline, where there are 3 on 100% natural gas, we would need slightly more than that for hydrogen. And for 100% hydrogen, 4.4 booster stations. So we would not only need to completely replace the compressor booster stations for 100% hydrogen, but we would need to have them at more frequent intervals as well. So if you'd go to the next slide, please. This is there's a bit missing at the top there. Not sure how that happened. So I can explain it. Anyway, so in the second column over, which is the figures from the tables you've just looked at, you can see 100% natural gas case, Genesis estimated 39 megawatts. For the 20% hydrogen case, they had 48 megawatts, and for the 100% hydrogen case, they had 170 megawatts. We've assumed that. Now, the third column across is where we decided to reduce those figures by Genesis did in-house calculations on this, so I'm not saying how accurate they are, I just don't know. But we took their figures and we reduced them by 10% because they included all sorts of auxiliary power requirements that you have on these sites rather than looking at the actual gas compression case itself. So the third column shows all of those figures reduced by 10%. And then in the fourth column, which is the important one, really important one, we got actual quotations from reputable compressor manufacturers of what they were able to offer using their own selection software. And you can see, whereas in the first case, this is an existing gas turbine driven pipeline compressor in the national transmission system, existing one, single train, 32 megawatts. It's one train centrifugal compressor of typical pipeline type that I'll talk about in a minute. And we couldn't, that was just the data that we had. So we looked at how we might do that that same duty in using electric motor drives, because there's very little doubt, I think, and I think this is generally accepted, that future pipeline compressors will not be gas turbine driven. They'll be electric motor driven, and so we followed that through in the rest of the thinking, and so we can see that we needed, for that particular application, we needed three centrifugal compressors, motor driven, and that came up with a total power of about 33 megawatts, so very similar to the gas turbine driven one. We then looked at the 20% hydrogen case in the same type of compressor, again, three of them, and that increased the power requirement to 40 megawatts. We then looked at three ways of doing the 100% hydrogen case. One with reciprocating compressors, which are in the hydrogen industry are the sitting tenants. They're almost all of the experience that there is in hydrogen compression is with large reciprocating compressors in the process industries. And for that duty, we came up with the vendor came up with a total power requirement of 120. Which is a lot less than the 170 that Genesis talked about, but still hugely higher than for the 100% natural gas case. And that even that required 6 complete reciprocating compressor trains. So this would be a very, very much larger installation than anything we're looking at the moment. And then we looked at using centrifugal compressors, although the experience isn't really there yet, but they're sufficiently advanced so that they can reasonably accurately estimate the power. And for centrifugal compressor between bearings design, and I'll explain that in a minute if you don't know what it means, came up with 129 megawatts. So as we'd expect, a bit more than reciprocating compressors in terms of power requirement, lower efficiency. And then we also looked at integrally geared compressors, which have the benefit of being able to run each impeller at the optimum speed for the application. And that came up with 126 megawatts, which was just between the previous two. So all that was in line with expectations. So yeah, the actual figures are less than were shown in the original report. But the important thing is that the differentials between them are not that different from the original report. So we felt that verified the report very well. Next, please. Right, now the reason for this is we need to look at the physical properties of hydrogen and those for natural gas. And if we could go on, please. So the main difference in physical properties between hydrogen and natural gas are as follows, and we've done this very comprehensively in Table 5 of the hydrogen compression report when you get a chance to see it. But I've just picked out the four most important differences. The one everybody will know about is the difference in molar mass, or what we used to call molecular weight. For hydrogen is just a little over 2. For natural gas is 19, and we used actual UK natural gas figures here rather than methane, as some people do. Methane's a bit less than that. So that shows just on weight alone, natural gas is 9 times heavier than hydrogen, and that gives all sorts of issues for the compressor, because heavier gases are much easier to compress than lighter gases, and there isn't a lighter gas than hydrogen. Another big difference is the isentropic exponent, or the ratio of specific heats, which for hydrogen is just over 1.4, very similar to air as it happens, and for natural gas is 1.282. Now, these might not look very big differences, but in compressor design, they are massive, because this is the isentropic exponent that determines what the discharge temperature of the gas will be, and whether there is a requirement for intercooling and aftercooling, which there would be for hydrogen and probably would not be for natural gas, depending on the application. But the other really important one, and this is what I'll major on, is volumetric energy. And I've already mentioned several times the importance of looking at the same energy flow. And you can see that the volumetric energy content is for hydrogen is just 10.4 megajoules per cubic meter, whereas for natural gas it's 38.03. So that simple arithmetic there shows you that you can transmit 3.8 times as much energy in the same volume flow of gas with natural gas as you can with hydrogen, and that is the main reason for the enormous differences that we've seen in the previous table. And finally, compressibility. This has some effect too. Compressibility of hydrogen 1 to 1.2, depending on the conditions, compared to natural gas at sub 1, and it just demonstrates that hydrogen is one of those gases that, put it in simple terms, just does not want to be compressed. It's one of the most difficult gases we've recognized for many years in the compressor industry. It's not to say it's impossible to compress, but it is certainly a lot easier to do in a positive displacement machine where you're physically reducing the space than it is in a dynamic machine like a centrifugal compressor, where you're relying on the acceleration and deceleration of the molecules of the gas to achieve the compression. So these are all things that have to be taken into consideration in any analysis. Next, please. So, as seen from that table, the main, not only reason for the very much higher flow rates is the volumetric energy, and I've talked about that, so won't repeat it. So this is not a factor, and I'm tired of having to say this to people, but this is not a factor that can be considerably reduced by more research and development. It is subject to the laws of physics. Of course, improvements can be made with compressors, and that's what we do in the compressor industry. But the main thing we're dealing here with is the laws of physics. Proposals, for example, to repurpose natural gas pipelines for ultimate use with 100% hydrogen must take these laws into consideration. Some other current reports appear to almost ignore the different physical characteristics of hydrogen or gloss over the issue entirely, which is why we're majoring on it in this report. Next, please. So hydrogen compression report, the compressor duties within the hydrogen value chain. Next, please. This is a sort of infographic that we came up with for the report, and I don't claim ownership of this. We based it on a concept developed by the Austrian valve compressor valve manufacturer Herbiger, who were of enormous assistance to us in the report, and have permitted us to use this. And what it shows is the hydrogen source on the left, the storage transmission in the middle, and the industry as the end users on the right. And you see the six compressor applications that we've picked there. And before anybody says to me, well, there are going to be more than those. Yes, I know that. There's an almost infinite number of permutations you could have. But to try and explain this, we've picked six, and we hope those are illustrative enough. In the top left-hand corner, you've got the production of hydrogen from renewable energy via electrolysis, and that creates the hydrogen, depending on the technology you use, somewhere between 1 and 40 bar. And the bottom left to right, you've got the production of blue hydrogen from steam methane reforming or autothermal reforming, and here the pressures will vary depending on the technology used, but there will be similar compressors in many respects for the green hydrogen, but it all depends on that suction pressure. Obviously, and you may not realize this, but a compressor operating at 1 bar suction will be approximately 40 times bigger than one operating at 40 bar. So getting that pressure up there is very, very important, and completely changes the type of compressor that you use. Anyway, we take compressed gas hydrogen at say 40 bar, going into either pipeline compression, operating at anywhere between 30 and 80 bar, or into storage compression, and here it'll have to be raised to much higher pressure, say 250 to 350 bar, and that will then be fed into a tube trailer, or ultimately into geological storage, as shown on the diagram. And the two compressors in the top right-hand corner are really fuel station compressors, either in the top one taking the feed from the electrolyzer, or in the one below it in taking the feed from a gas pipeline, if you happen to have one available. Again, the big difference in those two is in the suction pressure, the inlet pressure of the compressor. Next, please. So these are the six duties that we're looking at, from starting with the largest ones, very high flow rate machines, the NTS pipeline booster compressors, working roughly between 30 and 80 bar. And you could say going down to the compressors for geological surface storage, also very high flow rate machines. They're going up to 300, 350 bar. Then between those, you've got the feeder compressors for blue hydrogen, feeder compressors for green hydrogen, and you can see that concern there on green hydrogen is is getting that 1 bar suction up to something much more commercially viable, because it really cannot justify compressing hydrogen from those very, very low pressures. And then looking at refueling station compressors, going again from electrolysis up to 350 to 500, or if the pipeline is there, from 30 to 70 bar up to 350 to 500. And that's the range we've looked at in the report. Thank you. Next, please. So compressor types used in the hydrogen value chain. Next, please. I've referred to these already, but let's just look at them in a bit more detail. Positive displacement machines, these what we have at the moment existing are reciprocating compressors, diaphragm, hydraulic, liquid piston, and rotary screw. And in dynamic machines, centrifugal, I don't see any likelihood of axial flow compressors being used in hydrogen application for a variety of reasons. And then in the third column, non-mechanical types, and this is still an area of development. There's nothing really existing in this area, but it's getting closer all the time. And this is the hope for the future, perhaps, in that we can have non-mechanical compressors without all the hundreds, thousands of moving parts, and do it all by chemical means. The three types are metal hydrides, electrochemical, and adsorption, desorption units. Next, please. So looking at, this is a typical natural gas pipeline compressor, and it shows a fairly simple compressor unit wedged in between two flanges of the pipeline. So it's all very neat. It's very it's very low space requirement. That particular version comes from Siemens, but there are other manufacturers in the marketplace, of course. Looking at a cutaway drawing of a similar machine, but this time from the Nuova Pignoni division of Baker Hughes. And you can see there that is a between bearings compressor design, because you've got a bearing at each end of the shaft with in this case 2 impellers in between, and you can get up to 5 impellers in a standard casing like that. Next, please. And this is the hermetically sealed centrifugal compressor, motor driven, with I mentioned earlier in the tables, which can do up to a 20% hydrogen blend. And this is a compressor called Mapico, which comes from one of my former employers, MAN, where I cut my teeth on centrifugal compressors. Next, please. So then we come to the horizontally opposed reciprocating compressor that I mentioned earlier, where we needed 6 of these to replace one traditional gas pipeline compressor in the for 100% hydrogen case. And this you see a typical eight throw compressor there on the right, and a version that we would use in the 3D drawing on the left, and it shows the compressor, the central crankcase with the pistons, the cylinders on the outer edges, with pulsation dampers above them and below them, and you can see each one takes up a very, very large physical footprint, and we would need 6 of those. And you begin to understand then how different these compressor stations are going to be. This particular one is from the Thomason division of Howden. Next, please. And this is a traditional between bearings multi-stage compressor, but designed for 100% hydrogen. This particular one is from Baker Hughes. And if we go on to the next slide, this is a very interesting graphic that I wanted to share with you for a couple of minutes, where you can see it along the top, the hydrogen blend in mole percent, ranging from 0% hydrogen, in other words, 100% natural gas in this case, all the way up to 100%, which is what we're aiming for. And it shows with a standard pipeline compressor, with the impellers running at a typical circumferential velocity or tip speed of 250 meters per second, you would perhaps in a given application need 3 impellers to achieve what the pressure ratio that you were looking for. If you were to, in the second row down, if you were to look at increasing that tip speed to 300 meters per second, which is going further than the process industry or the American Petroleum Industry Institute standards would want you to go at the moment. So there's some considerable rethinking to do there. You could reduce that to 2 impellers. And if you went for very much higher tip speeds, going all the way up to 450 meters per second, and it's not that we haven't been able to do that before, but the hydrogen or process industry is very, very conservative. And I think it will be quite a number of years before API will allow us to do that. You could actually reduce that impeller on natural gas to just 1. And then you see going to the right of those numbers, the number of impellers you would require for each increase in hydrogen blend in the natural gas. And I think you can see that if we're working at the standard tip speeds, then a difference of 3 impellers to go to 28 impellers would require a total rethink of how we do hydrogen compression how we do compression for 100% hydrogen. So that I'm not in any of this suggesting that this cannot be done. I think technically it certainly could be done. And the real issue is going to be the commercial viability of doing this. But whether or not it can be done, these are things that if we're looking at going to 100% hydrogen and want to use dynamic compressors, then these are things that we have to take into account. Next, please. So this is the integrally geared 8-stage machine that we used in our report. You see the plan view on the left, and here's an example of the compressor on the right. Now it's a little different from what we would use. This was the photograph I had. It's a little different from the one we would use in the hydrogen application, in that we wouldn't be using all of these intercoolers, the big yellow things that you see in the left part of the picture. But it does show the size of the compressor, and you can see the which is the bit standing on top of the table foundation, and you can see from the size of the guy working on it there that this is a very much bigger application than we see in present configurations, and we would need 3 of these to do that 100% hydrogen duty. So just to give you an idea of the scale. Next, please. Right, just looking at some lower flow positive displacement compressors, and this is this is easier to do because it's we can purpose design these for 100% hydrogen from the beginning. And here you see some of the options that I mentioned in the introduction. That on the left, a vertical reciprocating compressor, the compressor from the Ariel Corporation in the United States, packaged by Herbiger that I mentioned earlier. On the right, a typical ionic liquid piston compressor package from Linde. Next, please. Here's a rotary screw using water injection in an oil-free screw together with the discharge water recovery system. This particular version from the German company Erzen, although there are other vendors, of course. Next, please. And here, a typical diaphragm compressor package from NEA. And on the right, from another division of the same company, a typical hydraulic compressor. I'm not going to say any more about these. They are all covered in quite a lot of detail in the report, so I'd encourage you to read the report. Next, please. And here, finally, the non-mechanical compressors, and I don't have anything more to say about them. We'll cover them in the report. I'd refer you to that. So next, please. Safety and sustainability, two very important aspects of all of this. Next, please. So section 6.3 of the hydrogen compression report looks at a number of safety considerations for hydrogen compressors, specifically containment, leakage and flammability, explosion risk, and electric motor drives. Now, this is a relatively brief summary. We haven't made it brief because it isn't important. It is super important. But we recognize that the Energy Institute is developing a number of other publications which are quite specifically covering safety in much more detail and across the hydrogen value chain. And I'd refer you to those. And we are in no way underplaying the importance of safety with whole hydrogen systems. It's absolutely crucial to its success. Next, please. So a whole section 9 of the hydrogen compression report is devoted to sustainability issues for hydrogen compressors. And although this is still a fairly unusual topic in most technical reports in the UK, the days when sustainability can merely be treated as an afterthought are over, and this should also always be considered in future. Sustainability issues covered in this report are materials of construction, manufacturing methods, and operating fluids. And you might say, well, yes, you're a sustainability consultant, and you would say that, wouldn't you? But really, without sustainability, we're being considered much, much more than we've ever done before. We're not going to be successful in this business. Next, please. Right, brief conclusions from the reports. Next, please. So these are by no means all of the conclusions in the report, but I just wanted to pick out some that are of general interest to people. First, repurposing of existing gas pipelines, which is a question we're asked all the time by all sorts of different people and groups. But the concept of repurposing existing natural gas pipelines is a good one, and I want to stress that. And in many ways, it meets modern sustainability criteria. For example, the UN Sustainable Development Goals, better than building a brand new gas pipeline where you've got the emissions and material usage of on a very much larger basis. Other studies focus mainly on and there have been quite a few studies into repurposing pipelines, but those studies focus mainly on the certainly important issues of mechanical and material integrity and other safety concerns of the pipelines themselves. But I haven't seen one yet that mentions the serious issues with gas compression equipment outlined in this report. Next, please. And so taking these issues together, a more holistic systems engineering approach to the idea of repurposing existing pipelines, together with a more realistic assessment of their real-world commercial and genuine sustainability impacts, is likely to generate considerably different conclusions. Next, please. So increasing hydrogen blends from 0 to 100%. The report mainly considers 100% natural gas and 100% hydrogen cases, and clearly shows that radically different compressor types are required for these two duties, and that the drive power physical footprint and both CapEx and OpEx will be very much higher, an order of magnitude in some cases, for the 100% hydrogen duty. And although the report considers only 100% natural gas, 100% hydrogen, and not intermediate blends, there is mention of the 20% blend, as I said before. But the case even for even a 20% hydrogen blend of hydrogen and natural gas is unlikely to be achievable in the same compressor. The implication of this is that completely new compressors would be required for every 20% step increase in the blend. Next, please. Hydrogen storage. I know some of you online will be interested in the storage aspects. Hydrogen compression for storage will be subject to similar physical constraints as those for pipeline transmission. Regardless of the type of storage, gas has to be moved from its production source to the storage location and then further compressed to much higher pressure, 250 to 350 bar for storage. It then has to be transmitted to its final point of use, which may also require additional compression stroke expansion facilities. The type and size of compressors used for hydrogen storage will be even more complex than for transmission due to the very much larger pressure ratios and differential pressures involved. Both the CapEx and OpEx costs, as well as physical footprint, will be considerably higher. And just to mention that whatever storage you use and wherever it is, it's not necessarily going to be in a convenient place for either production or usage, and so you will need pipelines to get you there to and from the storage place. So next, please. So future hydrogen compression technology, well, at smaller scale, we have looked at some of these things in the report. At smaller scale, there are various existing suitable mechanical technologies and multiple vendors. The main requirement for this sector will be making a compelling, internationally agreed safety stroke sustainability case for their use in 100% hydrogen duty. Non-mechanical compressors are in development, but it is much too early to know what impact these will have on the market at this stage. And at larger scale, reciprocating compressors are the only well-proven technology. There is an understandable desire to use centrifugal compressors in high flow rate applications, lower maintenance, higher availability, etc. But the length of time needed to make safety and commercial cases for these machines is unknown, as I've explained in the course. I think that's it. The next, please. Yes, thank you. Many thanks for your attention, and I'm sure there will be some questions. Thank you.
Thank you very much, Ian. Yeah, so if everyone else doesn't mind, so we've got some questions in the Q&A function, so I'm just going to go in the order that they're there. So there's one called, there's one where it says, in relation to extra requirements for H2 versus natural gas, will we not be moving significantly less energy in a future hydrogen network compared to natural gas today? Future hydrogen consumption will be far less than natural gas consumption today.
Of course, that is a possibility. but we just don't know, do we? And I get this one played back to me quite a lot. So I think whether that is the case or is not the case in the future, I think you have to decide up front what it is you want to do with hydrogen. I think we have a bit of a problem in this country, in my experience, in energy policy, in that we're very good at saying what we want to do, but we don't actually quantify what we want to do. So in the absence of that quantification, we decided that we would look at what about if we want to transmit the same energy flow? Because I'm not sure. Obviously, if you say, well, we'll try and do it through existing pipelines, then you would be looking perhaps at a quarter of the energy flow. And perhaps that may meet the needs, but you're still going to have radically different compression requirements from what you've got at the moment. So I don't think to simply say, yeah, but our gas requirements in the future will be less, so it doesn't really matter. I don't think that's a very realistic way of looking at it, frankly.
Good answer. So the next question we have is, what limits top speed in a centrifugal machine, and what technical challenges would need to be overcome?
Yeah, it's a good question. It's mechanical integrity, really. The type of impellers that I showed you in the presentation were a mixture of what we call open impellers and shrouded impellers. And working at those speeds, shrouded impellers are likely to, or not likely to, that's an overstatement. They are, the concern is that they could, the mechanical integrity would not be sufficient for them to remain whole, and bits would start coming off them. The shrouds would start coming off. So we are looking at very, very serious issues here with consequences, which is why the American Petroleum Institute has for decades now kept tip speeds very low, very conservative. Mechanical integrity has improved greatly over the decades, and I'm personally comfortable with designing compressors at 450 meters per second, but I don't think the industry is yet, and that's where the market is.
Thank you very much for that, Ian. We have another question that says, could you compare heat pumps with using H2 from a technical, economic, and legal feasibility point of view? Also, for acceptability.
Yes, I could have had a couple of hours to spare. I think it does raise an interesting question in that we've decided in this country that for domestic heating, and I guess that's where the question is really coming from. We've got this binary choice between heat pumps, or particularly air source heat pumps, and hydrogen boilers, and I think both it's clear that both hydrogen boilers and air source heat pumps have got a huge number of issues to overcome. I'm really concerned that we've made it that binary choice, and that's all we have. I think there are other ways of heating homes which offer you much more flexibility, much more possibility, and so for that reason, I think it's a bit of a fruitless comparison, because we're just not we're not going to meet our targets if we're going to rely on just those two ways of doing things.
Thank you for that, Ian. So the next question is there a typical limit for hydrogen water content or dew point for the compressor design for 80 barge pipeline compression? How is this managed for higher pressure compression to 350 barge storage?
Yeah, well, the short answer to that is that's as long as the wetness fraction in the gas is known, and the compressor manufacturer is aware of that, that can be taken into account in the compressor design. My experience is that some users don't tell the compressor manufacturer all of these facts, and that often runs into problems. But yes, if it's upfront, it's known upfront, and it's divulged, it can be accommodated in the design.
Okay, great. I think we have a couple more questions, and then yeah, we're pretty much on time. So another question from the Q&A function is, are you assuming the same energy flows in the gas transmission and distribution system will be required?
Well, I think that goes back to the previous question. I'm not assuming anything. I'm saying the only way you can since nobody knows what the future requirement will be, you can only really evaluate it on what we do at present, which is the amount of energy that we need in our gas pipelines at the time. Of course, if you come up with different needs, then that can be assessed separately. But you can't really do a general report based on some variable figure.
Okay, great. We have another question in the chat. It was told earlier, or you were told earlier in the presentation, that centrifugal comp can suit the H2 blend only up to 20%. How much would number of impellers increase using, e.g. EM comp? Can we decrease number of necessary components by using a newer comp?
I'm not sure I completely understand the question, because I think I explained from the Baker-Hughes diagram, and Baker-Hughes is a very, very well experienced company in the compressor business. The laws of physics require much more, many more impellers, as you saw from the diagram, for 100% hydrogen than they do for natural gas. That's just a fact. And I'm not sure that, I mean, yes, I'm sure different compressor vendors will come up with new solutions, but they're not going to change that very much.
Okay. I think that is the last unique question we've had. We had a different one about heat pumps. Well, we have one here. It might have been answered already, but if we start using hydrogen for heating homes in the UK, what changes or upgrades will be required to be done to the gas network or people's homes?
Yeah, well, that is a very open question. I think, and is way beyond the scope of the hydrogen compression report. And I think if you'd asked that question 5 years ago, you'd have had a very different answer from if you asked that question today. In that, hydrogen for domestic heating is much less popular now than it was a few years ago. So I can't really answer that one. It all depends where the public mood takes us.
That's fair. I believe that's the last question we've had today. Thank you everyone for staying on. I think we've still got about 50 odd participants left. Tim, Tony, Ian, do you want to say any closing remarks?
Yeah. We'd just like to thank you very much, Ian, for that very informative presentation. And also, just to everyone else, that we always have webinars such as this very one every so often. So if you would like to join more, please just look onto our what's on page onto the Energy Institute website, just to be informed. Otherwise, thank you so much, everyone, for joining for today. I guess we can draw it to a close at this point.